Welcome, everyone, and thank you for joining us for today's webinar, Using Ontologies to Guide Knowledge Graph Creation. My name is Amanda, and I'm part of the virtual events team here at Neo4j. And I'm thrilled to be joined by Jesus Barraza, AI Field CTO at Neo4j. We are super excited to have you all with us today. Just a quick note about questions before we get started. We invite you to submit any questions you have throughout the session using the Questions tab located at the top of your screen. We'll answer as many questions as possible at the end of today's presentation. And if we don't get to them all, someone on the Neo4j team will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. So with that, I'll go ahead and hand it over to Jesus.
Thank you very much, Amanda. I'm really excited to be here and to talk about one of my favorite topics, which is ontologies, and of course the role that they play in the construction of knowledge graphs, with of course with the help of LLMs and GenAI these days. I mean, we could not ignore that for a minute. So yeah, my plan is provide kind of a bit of an introduction, because I understand that the topic of ontologies and knowledge graph creation is probably familiar for most of you, but maybe just to level set, I'll spend a couple of minutes describing what an ontology is, and then take it from there. So let's start with a basic definition that you might have read here and there. So an ontology is basically I would say it's a domain model, and by a domain I mean kind of an area of expertise. I mean, it can be a model of a telecoms domain. It might be a model of the life sciences domain. It can be of finance. It can be any. It's true that ontologies sometimes can be used to, let's say, to describe higher level concepts, but I'm going to keep that out of the out of scope for today. So we'll focus on ontologies that describe specific domains, like I was mentioning at the beginning. There's an important thing about ontologies, though, and it's the fact, as you see in the description, that they are explicit and formal, and sometimes shared. I mean, it's common that we define ontologies with the intention to share information, to enable interoperability, as we're going to talk in a minute. But the critical thing, I would say, is that they are formal. And by formal, we just mean that they are machine readable. And that's critical, because we're going to be using them through tools for creating knowledge graphs in this case. And that's why it's key that this description of our domain is expressed in a form that we can consume and apply to a number of processes. So this characteristic is very important, as we're going to see. And what's in a domain model? I mean, what are the key elements that we will want to use to describe, again, these telecoms domain, these life science, pharma domain, this finance domain? Well, we will use things like categories, like classes. What are the types of entities? We sometimes call them node types that exist in my domain. That can be, for example, customers. What's the notion of a customer? I mean, if you're building an ontology for let's call it in the e-commerce domain, you will have customers, you will have purchases, you will have products. Right? This is the kind of thing that categories, classes represent. It can be locations. I mean, all these sort of things. In addition to the categories that exist in your domain, you will also have properties that describe these categories. For example, we refer to properties as attributes sometimes, or characteristics of these categories, and they can be, well, customers have customer IDs or customer names. Products will have product descriptions. A location may have a latitude and also a longitude. So these are kind of attributes that characterize the categories, the classes defined in an ontology. And finally, the third component that will commonly be present in your ontologies is the relationships. How do these entities relate to one another? This can be also referred to as connections or between the categories. And examples of those could be, for example, like I mentioned before, in an e-commerce domain on ontology, you may have a connection between customers and product, as in a customer purchases a product, or a product is part of a category. So this is the kind of basic primitives that you will find in an ontology. So an ontology is a domain description built on these kind of building blocks. Now, it's true that an ontology can be enriched with additional elements, and And these can be of different types. So for example, we can have instance data. Sometimes the ontology comes not only with the notion of a location, but it also comes with an enumeration of the locations. In this case, for example, countries, right? So I know that there's a limited, well-defined list of countries in the world. So rather than just defining the notion of a country, I provide an enumeration of all possible values. That's a way of kind of ensuring a certain level of data quality, because I already provide a list of all possible values or possible instances, if you want to refer to them like that. In the same way, if I define the notion of a product and I have a product catalog with my whole list of products, I can provide this, and this is typically referred to as reference data. It's like data that is low changing or immutable in certain cases, like I'm not saying that there's no new countries in the world. We have seen that, but it's a slow changing data, and it provides kind of a sort of a scaffolding for your the data you will populate using the ontology. So you can have instance data. That's one thing. You can add additional actions to your ontology, and by actions, I don't want to use fancy words, but it's like a more kind of rules, if you want, to enrich your collection of categories. For example, you might say that something is a subcategory of another thing. So, for example, I've defined what a customer is. Well, there's the notion of a gold customer or platinum customer, whatever we want to do, and this is a subcategory of customer. So we organize things in a kind of taxonomical organization that happens very often in life sciences, in pharma, and well, we might say that that brings bad memories from back then, but the SARS-CoV-2 virus is a subcategory of coronavirus, if you remember that. So it's this idea of saying that things are organized in taxonomies, and that's another way of enriching your ontology. And finally, you can add even more annotations to relationships. Like, for example, this relationship is transitive. Think of LinkedIn. Well, actually, for transitive, it might be a dependency, right? Depends on is the example there. If something depends on something else, and this something else depends on another thing, this indirect dependency indicates that the first element depends indirectly on the third. So it's kind of the notion of transitiveness as well. But I was mentioning the LinkedIn connected is symmetric. Symmetric meaning if I'm connected to X, X is connected to me. So if I'm connected to Amanda in LinkedIn, she's connected to me. That's not true for the following relationship in LinkedIn. So you can follow someone and not be followed back. So this is an important annotation that enriches the meaning, the semantics of your domain model. So these are the most common building blocks that you find in an ontology. So that's how you define your domain. But the interesting thing is, why would you want to do that in the first place? And I kind of hinted at it at the beginning. And I said that, well, often when you define and formalize a domain model, is because you want to agree with someone. And that in technology, of course, means we're probably going to be exchanging data. I'm going to be presenting my data according to terms that I want you to know and understand, so that the communication can be easier, right? That's what we call interoperability. So basically, I'm going to define an API according to a particular terminology defined by my ontology, and that will simplify the integration. So interoperability is one of the main drivers of the use of ontologies. But often we can use them for inferencing, and that's probably this final part that I mentioned at the beginning. Sorry, not the beginning, at the end, in the second slide on the elements in an ontology. Think, for example, of the transitive nature of certain relationships. We know that if something depends on something else and this depends on something else, then there's an indirect dependency there that I can derive, even if it's not present. I know that the transitive nature of the depends on relationship can be propagated, and I can find dependencies that are not explicitly stated, but I can derive. This is inferencing. This is a simple example of inferencing, right? So that's another way in which ontologies can be used. So some examples of ontologies. So there's a bunch of, you can of course create your own ontologies for your domain, but there's a number of them existing out there, and you can have a look at those. In finance, for example, the popular one is the FIBO ontology, the financial industry and business ontology, that defines a number of terms and relationships and properties, just like we saw a minute ago for the finance industry. And we're going to see a little example of it there in a moment. There's the schema.org, which is a pretty general one that defines very popular entities like, what's the notion of a person, what's a product, what's even, it's for web publishing and for annotation of web pages, but it's another very popular and very widely used ontology. And finally, I mentioned life sciences, but another one is the MESH vocabularies. I think MESH stands for medical subject headings, and it's published by the National Library of Medicine. But it's basically a terminology. They don't refer themselves as an ontology, but it's formalized as an ontology that provides a collection of terms that are used to annotate things like NLM databases and others. So these are just some examples there, but there's many others. And normally you will be building your own for your domain or reusing parts of these. Now, what does an ontology look like? Because we want to use them. Remember that this introduction is just to understand what ontologies are like, to understand how I can use them to create a knowledge graph driven by the ontology. So let's take the example of a small fragment of the FIBO ontology, the financial industry and business ontology. So this is one possible serialization. So ontologies can be described formally, so they have to be machine readable, but they can be expressed in JSON, in XML, and any other formalism. And this one is called Turtle. And here we see that there's a definition of what a privately held company is. And you have a text definition of it. But interestingly, in there, I don't know if you can see my mouse pointer, but you see that here at the top, it indicates that it's a subclass of a stock corporation. So this is kind of this idea of taxonomy that we were saying before. In the same way, a premium customer was a subclass of a customer, is a specialization of a customer. Well, a privately held company is a subclass of a stock corporation. If I keep exploring this definition, I see that a stock corporation is something, and I don't want to go into the details of this language that we're using here, which is OWL. You see that a stock corporation is related to a board agreement through the relationship is governed by. So those of you who are familiar with graphs are already starting to see kind of nodes and relationship here. And finally, it describes what a board agreement is, indicating that it's a class and what the definition of it is. But yeah, that's what it looks like if I presented it as a graph, right? So we see that a privately held company is a type of stock corporation, right? So it's a subclass of it. And a stock corporation is related to a board agreement through the is governed by relationship. Anyway, just to see that this is a description of a domain, a portion of the description of the finance domain by defining some key categories in this case, or classes, and how they relate to each other. Now, this is formal language that can be parsed and that we can use in many different ways. So how can we use them for knowledge graph construction? Because that's ultimately the objective that we're trying to achieve. And this is an example of the interoperability kind of use that we were talking about before. So the idea is that the ontology defines the structure of the target graph that I want to build, right? So that what I'm going to be doing with the ontology is using it to drive the creation of a data ingestion pipeline. So basically a script, if you want, or a way of channeling data into the graph so that the resulting graph is exactly the one described by the ontology. That's the idea. Now, depending on what your source data looks like, this process of moving data into the graph is going to look different. So let's say you have structured data in a relational database, in a collection of CSV files, in the output of an API, in a document database. So what would that look like? Well, this would be the traditional ETL, if you want. So it's sort of a structural mapping kind of rules. You can think of it. It's like saying, okay, this table, the table customer, is going to populate the nodes of type customer. And the mapping is going to be column X is going to populate property Y, column Z is going to populate property blah, 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 and so on and so forth. So it's kind of a more of a structural translation between what's in your source data and what's in the ontology, which we've seen are nodes, relationships, and properties. And you will see things like, yeah, I was mentioning a table or a projection or a document in your database will map to a category or to a node type. You can have maybe a foreign key in your relational database mapping to a relationship type. So you will derive relationships out of it. Or you can have columns mapping to attributes or even keys if what you have is a document instead of a table. But that's the idea. So you see it's kind of a structural mapping between source and target. And what that looks like is something like this in a simplified sort of data ingestion kind of pipeline schema or simplified architecture. So we have the tabular structure. Think of it of tables or APIs or files, doesn't matter. Structured data source. You have to inject what the target schema is, and you have to map it somehow. And we'll see that there's different ways to do that. And then once you have that mapping, you can write to the knowledge graph. Now, if your data is unstructured, then the process is going to be slightly different. And here I'm focusing specifically about text data, so natural language text. These can be documents, or it can be the transcripts of videos or audios, but this type of data, right? So it doesn't have the structure of a table or of a document. Document, as in JSON document, is more of a human natural language document. And in that case, we're going to do a different thing. We're going to try to either understand the structure of a document and generate a graph out of that, or extract entities and then disambiguate them if needed, and create a graph out of that. So it's a much fuzzier, if you want, a much less deterministic approach. And here's where LLMs and GenAI play an important role. And the way we do that in Neo4j is as follows. So let's say we have a collection of documents as in natural language documents. It can be PDFs, it can be anything. And we're going to build actually two graphs. The first graph is going to be what we call the domain graph, which is the one that's described by the domain ontologies that we've been talking about before. And in this case, we see that it describes a person that lives in a place. So persons, locations, exactly the type of things that we describe in an ontology. But we're going to enrich that with a model that describes the structure of the document. We call that sometimes the lexical graph. So this is just a way of representing the information in the document, as in the simplest case, if it's just text, it can be a sequence of portions, a sequence of fragments. But if it's a rich document that have let's say a structure in the form of chapters or sections or subsections, you might have a richer representation, maybe in the form of a tree. So these two graphs are layered on top of each other. And it's important because this dual representation will give you more options for retrieval and for analysis and for querying of the graph. But we'll put that on the side because we're focusing in this webinar on the construction phase. So what does the pipeline look like in this case? And I realize it might be a bit less readable. It's a bit small there. But what you do is you take your document, you load it, you split it if needed, as I was saying, in paragraphs, in sections, or in depending on the nature of the document. And then you inject again the ontology. That's the schema step. So you have to provide what's the target schema, the target ontology, the target domain model, so that you can do the entity extraction in a way that then you build the graph like the one that you have on the screen. Now, very important, we've talked about ontologies, and this is my own manual sketch there. It's important to understand that, yes, often ontologies will be described according to W3C standards. We saw OWL a minute ago, but these are machine-readable formats. And by definition, an ontology is an implementation-independent model. So you can use it to store data in Neo4j, to store data in a relational database, to store data in a triple store, whatever you want, because this formal representation of an ontology can be translated into multiple materializations that you can use, like I was saying before, for different processes. And in particular, we can think of if I want to import structured data, and this is a screen capture of our data imported in Aura, you can use the ontology, have it represented as a visual kind of graph of the schema, pretty much like we saw before, and then you can map the source data to your target ontology and get that graph populated into Neo4j. In the same way, you can take the ontology, and that's exactly what I'm going to demonstrate in a minute, and use that ontology to kind of inform the entity extraction tool. In this case, is the LLM graph builder which is kind of a visual environment, but you can use it also in the GraphRAG package that our engineering team builds if you want to do it programmatically. And again, use the same ontology to drive the entity extraction in that process. So because I'm not going to have time to dive deeper in all the possible options, I wanted to add a few references here to a series that we've been running for a few months, myself with some colleagues at Neo4j, and you have the link there to the GitHub repository, because there you have all the recordings of all the sessions, and that includes all the assets, the ontologies that we've used, the code that we've written, and these are guided examples on how to do exactly what I just described. So use an ontology to drive the extraction of structure out of unstructured data to build a knowledge graph. And that can be done from unstructured data in a no-code approach. So just drag and drop, click and run. And also in a programmatic approach. So whatever you do through the UI, as we're going to see today, you can replicate through code. And the same applies to structured data. And I have added here the references to the chapters, specific chapters or episodes in each of the series, where you would find the details on how to approach those. And they're all, like I was saying, in this GitHub repository that I referenced to here. So that's the idea. That's what the detail. But what I wanted to do before we conclude is run a demonstration of what this process looks like. And for that, allow me to stop sharing and go to my demonstration environment, which is basically the other browser. I hope the demo goes well. Here we go. I hope that's visible. And what we see here is it's one demo tool that our teams have created, which we call the LLM graph builder, knowledge graph builder. And basically, it implements the construction of a knowledge graph out of unstructured data. And in this case, what I'm going to use is a collection of text documents that contain information. I'm going to show them in a minute. That contain information about, I'm going to browse it, and actually I'm going to kick it off and talk why it does the input. So as you can see, these are text documents with the description of artworks in the Tate Modern Gallery here in London. So these are basically paintings by David Hockney and by Picasso. So these are just text description, which I'm going to load into my knowledge graph builder application. Now they're available they've been parsed, and we can now generate a graph out of them. And this is connected, the knowledge graph builder is connected to my Aura instance, which is empty here. So I have emptied, let's make sure that there's no data in it. So let's make sure I make no mistake, but there's note. Oh, of course, there's notes, because it already has the documents that we've just imported. Here we go. So when you parse these documents, as you can see, for each one of them, it will create a note representing the document and with some metadata about it, the name, some timestamp of the creation, etc., and the model that has been used. But other than that, it's an empty database. So what we're going to do is a first pass of what would it look like if I created a graph without providing any kind of guidance. So I've not given any ontology to the LLM. That's basically, as you can see down here, using OpenAI GPT 4.1. So what's happening is that an LLM is analyzing. Well, before the LLM, it's actually implementing the pipeline that I was mentioning before. It's parsing the documents, it's creating the chunks, it's vectorizing them, but then it's extracting the entities using OpenAI GPT 4.1. But it's doing it blindly. So it's going to come up with whatever it finds in there. And we're going to see that this is not a very good idea. It might be in some cases, when you're going to be, you're in exploratory mode, but you're going to see that the graph is a bit confusing because it finds all types of entities, right? So you will see, for example, that there's artworks, there's articles, there's characteristics, there's, it thinks that anything can be an entity, and because we don't give any guidance, the graph that is being created is not particularly useful. We're going to see in a moment. But I wanted to show an interesting feature of this application, and that's the fact that we can preview nicely. Okay, that's some analytics features that will be available later. So it's nearly done. Here we go. So it's completed the extraction, and now we have we should be able to preview the graph, and it's going to preview the schema. Well, that's not very easy to. Okay, I'm going to go to Neo4j then, because here it's a bit hard to read. But that's exactly the whole point, right? Because what it's done, it's created all sorts of entities, and you will find things that are often unexpected, right? So look at all the types of entities that it's found, and you will find things like, for example, let's see, let's look at the attributes the attributes, the relationships that it's created. So it's actually how many? You see there's 990 something, but okay, authored. Let's look at one, authored, because it's artwork, so maybe we can get something there. And I'm gonna have to change a little bit the presentation so that it's more readable. Let's put this at the bottom, and we see these are publications. We can use the ID for this. Okay, so it's a bit not great in the sense that it's doing things like telling me that Marco Livingston, who seems to be a person, has authored David Hockney, which doesn't sound right? Because it's, you would expect it to author an artwork rather than another person. But and you can check that with rules, right? You can use Cypher for that. So you can say, okay, I would expect that whenever you find a person that's authored, I don't know if this is going to be readable. I hope it is. I'm going to try to make it a bit bigger and hide some elements here to make it. But anyway, so I was going to say that you can check that whenever a person has authored something, that something, you would expect that to be an artwork, right? So if X is not an artwork, so when that is not true, am I using it right? No, I don't need the parentheses here. So if that is not true, maybe return X. So basically what I'm saying here, and I'm improvising this kind of rule, I'm saying if there's a connection between a person and the relationship authored, we can add the arrow, this thing should be of type artwork. That's the natural thing. But if it's not the case, then, well, maybe erase it as a, we can put here P, put the person, and the other value. And we see that there's some violations in this case. So for example, we see that there's cases like, for example, a person creating another person, which is, again, one of the consequences of leaving the LLM freely extracting things that it finds without any kind of guidance. So not very good quality data, what we're getting. So what I'm going to do is I'm going to empty the database again, and this can be done easily by telling to delete the files, and these will delete the entities in the database, and then start the process again, but this time providing the guidance of an ontology, right? So hopefully this should have created, deleted all the, let's see if we should have these in the history. So perfect. So we're back to 0 nodes. So the graph database has been emptied. And now what I'm going to do is I'm going to use the same files I used before. So no change to that. I'm intentionally excluding that, not that they're big at all, but because we're in a live demo, I don't want it to take more time than needed. So it's reloading the files again. But before I click generate the graph like I did before, I'm going to use the graph enhancement. And here I can provide some kind of guidance in the form of an ontology. I can say, well, these are the kind of patterns that I want my graph to follow. And I'm going to use a format that I've downloaded, hopefully here. It should be in my downloads. There we go. So that's the art ontology. And we see these kind of statements. So we see that my ontology defines the notion of, okay, an artwork is created by an artist. An artist can influence another artist. An artist can work with another artist. And like this, I'm enumerating the type of valid relationship and valid types of entities that I'm expecting to find in my data. So I'm applying this. And this is kind of the guardrails. I know it's limited, and this is going to capture just a portion of the data in my source, but it's a way of keeping control over the structure of the graph that's being created. So I'm going to run exactly the same process now, and it should take a few seconds like before. But now the graph is going to have the structure that my ontology describes. And like this, I can anticipate the kind of queries that I'll be able to write. And I know upfront that there should be artist. Oh, no, animal. That's from the previous execution. I know that there will be an artist that influences another artist. Oops. So there's a relationship that's that's still not, probably as it's loading, it's still not refreshing the autocomplete influences. There you go. So we'll find patterns like this one. Let's call this pattern P. And I'm going to return that. Let's see how it's doing. There you go. So it's nearly completed. Oh, no, it's still processing the last two. But we should find these type of relationships, because that's exactly what my ontology defines. If I look at the schema now, it should be a lot simpler. So there's, well, I don't know why it's replicating some of them, but you see that an artist influences another artist. I don't particularly like this representation, but we can look at that in Neo4j directly. So if I run this query, I should now find, there you go. So the kind of, like I did before, I need to modify the order in which styles are applied. But you see how there's a clear chain of influences in my graph. And the entities that I find are controlled by my ontology. So I have artworks. So if I expand, or in the same way, I can say, well, I want to know, I think the relationship was created by, or what was it? No, I can't remember what was the entity that was. We can see it here. Was created by, so we can do it here. It won't be an artist, it will be an artwork. Why does it not help me autocomplete? Was created by. Or was it not was? I mean, maybe I'm not using the right. Yeah, was created by. That's the right. Was created by. And we should get the artist here. So hopefully that's worked. Some spelling mistake, of course. That's not good writing. That's why it was not doing it, because I'm using a very weird cipher there. I was using the notation of a node for a relationship. There you go. So we find things like the artworks by a particular artist, and we see that the relationships and the types of entities are exactly the ones defined in my ontology. So that's how important it is to provide these kind of guardrails. And now, the powerful thing here is that we can, once we've created the graph, we can interact with it. And just as a simple example here, I'm going to show how we can interact in a conversational fashion and say, which are David Hockney influences. Let's see if it can come up with an answer to that. And there's some additional features, but yeah, there you go. It's influenced by Matisse and Picasso. And the powerful thing is that if I look at the details, it will tell me which are the entities that were used. And we see that there's artwork and artist. And if I look at the portion of the graph that was used, it will show me how the influence relationship was followed to answer that part of the question, right? So that's the explainability that we get from being able to use a structure and curated knowledge graph, knowledge source, like a knowledge graph here. So right, so I'm conscious of time, so I just wanted to show briefly, the difference in data quality and the resulting graph of using an ontology and not using it. So let me, just to conclude, go back to the deck, and let me stop sharing for now. Screen, stop sharing, and go back to my slides just to conclude. So boom, hopefully you can see it back, and we can go to the takeaways from this session. So the first one is that ontologies can take many different forms, and you have to use them. And we shown in this example, very briefly, you'll see the detail in the many sessions that I refer to, but you've seen how I started, I did that offline, but you have an ontology that's been created with any ontology development tool, and you can transform it into something that Neo4j can import, can use to drive the behavior of the knowledge graph builder in this case. But the same applies to our Aura mapping tool and to our GraphRAG package. So that's important. The second one is we should avoid the blind knowledge graph construction. So always use an ontology driven approach, because that will give you the control over the schema and the target graph that you create. Then in addition to, we didn't touch on that today, but it's important to combine unstructured. So using unstructured data has limitations in the sense that you need to somehow provide the scaffolding that some reference data adds to it. So in this case, we have extracted the name of authors, right, and artworks, an artist, I think it was in this case. But if we have a list, a reference of the the catalog in the Tate Modern, which is the source of the data that we had, maybe we should be able to have a much better linked data. So the combination of structured and unstructured will definitely be best practice in this case. And this can come from an ontology, or that can come from some unstructured data, like I was mentioning, like a catalog or something like that. And finally, ontologies can be used for data validation. So the kind of query that I improvised and saying, hey, when you have an artist that creates something, this something has to be an artwork, that can be derived from the ontology. And it's a way of checking, the structure that you're creating complies with your, if you have a single data ingestion pipeline, that's kind of guaranteed because you build it into the process. But if there's multiple pipelines writing to your graph, maybe you want to have control in that particular way. But anyway, I hope these are some takeaways that you live with. And with that, I'm going to hand it over to Amanda for Q&A if we have any questions coming from the attendees.
Awesome. All right. Well, thank you, Jesus, for such a great presentation. It looks like we do have some time for a few questions. I wanted to remind the audience, if they'd like to submit a question, they can do so by typing it into the questions tab at the top of your screen. If we don't get to all the questions, someone on the Neo4j team will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. So we did have some questions come in throughout the presentation. So let's get started with some of those. I'm just going to go through them. All right, this is a great question. This individual is asking, are ontologies only relevant for knowledge graph creation? What about for retrieval? Do they add any value?
Yeah, good one. So that, yes, they do. The answer is yes. We focused on the construction and we showed how they provide this kind of guardrails to the kind of graph that we're creating. But I didn't go deep into the retrieval step, but there's multiple retrieval strategies. When your natural language interaction with your LLM gets translated into something that retrieves data from the graph, there's multiple options. So one is, like we saw now, you can do a vector search and find some matches and then navigate the graph and contextualize. But another thing that you can do is, or another technique for retrieval, is to try and generate some structure query. So in our case would be generating cipher, so text to cipher. And in order to generate high quality cipher, we need to have an idea of the structure of the graph that we're querying. And if you give me an ontology, the ontology typically comes with a description of each of the elements that are there, the classes, the categories, the relationships, the properties, and with textual description of each one of them. So that's exactly the role that ontologies can play. They can provide information on the structure of the graph so that the quality of the cipher generated is higher. If that's not present, we can always, because Neo4j is kind of self-descriptive in the sense that you can go query and give me the list of nodes types and relationship types and properties. But it's not as rich a description as the one that you would get from an ontology. So yes, they can definitely enhance the quality of the cipher generated in a text to cipher translation step.
Awesome, thank you. Moving on to the next question. Can we use OWL/RDF ontologies directly in Neo4j?
Yeah, so that's the bit that I was mentioning that I kind of hid a little bit, because I didn't want to show the whole process. So the answer is not directly. I mean, practically yes, but you cannot, for example, at a moment when you probably saw me importing the ontology, and when I was doing the knowledge graph creation, I used really kind of a translation from the OWL ontology. So initially my ontology was created. I typically use Web Protege or Protege, which is the open source or the free ontology development tool by Stanford University. And I save it as an OWL ontology. So yeah, that's an entirely W3C standard one. But then I had to translate it into a format that the knowledge graph importer understands. But this translation, and that's why I insisted at the beginning on the formal nature of the description of an ontology. It's kind of trivial because it's just a question of rewriting it in a format that the LLM knowledge graph builder understands. So strictly speaking, not directly, but the code and again, it's in the references that I shared as part of the episode. You will get scripts that can translate that in a way that's directly usable.
Awesome, thank you. And it looks like we have time for one more question today, so we'll end with this. Can LLMs help in the construction of ontology?
Oh, that's a very good one, and it can be maybe controversial to some, because as we mentioned at the beginning, sometimes in the ontologies are by definition shared, so are the result of consensus, and therefore it's different parts, different individuals, different knowledge experts. But if we put that aside, which is I think humans need to stay in the loop. Yes, LLMs can be very good assistants in the modeling process. So we have I didn't mention it in the presentation, but we have examples in the Going Meta series where we experimented with this idea. Like I provide a data set in the form of a denormalized table, and why don't you try to distill a graph model or an ontology out of it? And the LLMs do a very, very good job at it. So yes, LLMs can definitely, I'm not saying that they will generate the perfect graph model that you will want to use, because modeling is an art rather than a science. So it will depend on the type of workloads that you want to run on your graph. It will depend on the type of analytics that you want to run on your graph. So maybe you will want to iterate on that. But LLMs certainly can provide assistance in the generation of models and formalize them as ontologies. Absolutely.
Awesome. Well, that's all the time we do have today. So thank you, Jesus, for being with us today. And for those in the audience, thank you for joining us today as well. I wish you all a great day. Thanks so much.
Bye. Thank you.